Hello and welcome all. Lecture 66, CFD application to design and performance assessment. So in last lecture we were discussing important aspects about the CFD. The question that was arise in sense why, what and how this CFD. Why in the sense why are we looking for doing CFD analysis for compressors and fans. So basic idea is very first case it is to be used for design purpose or design assessment. Second, that's what is performance assessment under different design and off design conditions. Then after, based on that study, if we are looking for something, that question is what exactly we are looking for. So how our flow, that's what is behaving within the blade passage, how the flow, that's what is behaving, is it as per our expectation or not. That means we will be checking with velocity components, flow angles, pressure distribution, total pressure distribution kind of situation. Now how, that means that's what is giving us answer in terms of analyzing the results what we have achieved by using CFD analysis. So this is what all we were discussing about, and in that case, based on my application, all these questions that what will be varying. So we need to be very careful for exactly which purpose we are doing our computational fluid dynamics analysis. Then for turbomachinery application, we have seen the development of CFD for over the year. Say initially it was started with 1D, then 2D, quasi 3D, 3D, now it is full 3D kind of analysis. So we have seen what all we have learned in that sense. Then after we have learned with the level of CFD analysis, that's what was initially started with potential flow theory. Then after 2D axisymmetric analysis, then it was say quasi 3D simulation, then it is fully 3D in terms we have realized say Navier-Stokes equation to be solved. It is RANS, URANS, maybe LES or DNS. So all those things we have discussed in our last lecture. Then we started discussing about the steps involved for the CFD analysis, in which we were discussing about initially to make the flow domain. Then that flow domain we need to divide into small volumes in order to solve those problems, or say in order to solve numerically the flow domain. For that we are looking for some kind of boundary conditions which are required. Then after we are looking for solvers, that's what is using our fundamental equations, say mass, momentum and say energy equation. And then we have realized after doing this say analysis, we are looking for post processing. So from today we will start discussing about how exactly we will be moving with these steps. So very first step, that's what is say we understand it is to discretize the domain. So let's see what is the meaning of that. Here if we look at, this is what is representing multi-stage axial flow compressor. Now we are having rotor, that's what will be followed by stator, rotor and stator combination. Now if we want to analyze such kind of flow domain, we must realize my volume will be very huge. In order to analyze that, we are looking for huge number of elements, number of small volumes. That means it required to have huge computational power. That's what is required, huge amount of time in order to solve that problem. So we were discussing, in place of analyzing say whole stage or say multi-stage configuration, we will be selecting one or two blades, like here it is shown. So here we are having one rotor, that's what will be followed by stator, rotor, stator combination kind of situation. So under that condition, that's what will be helping us in terms of reducing the number of elements required. Now when we say a number of elements required, that's what will be reducing, that will help in terms of saving our time and computational power. So in order to do that thing, we need to have certain understanding, we need to have certain terms and condition to be followed. then only we can analyze such kind of situation. Let me tell, say here, this is what is, say we are having stator, that will be followed by rotor, then stator, rotor and stator combination. So under that condition, if we are looking at, this is what is representing one of the domain. Suppose say this is what is a stator domain, we can say it's a stationary domain. Now here this blade, it is placed in the center, and what surface we are observing on, say our right hand side and left hand side of this blade, we can say maybe on suction surface and say pressure surface. Based on the pitch, we need to make this domain ready with. So here in this case, what calculation, that's what is numerically we are solving, that will be getting exchanged to next coming domain, and that's how we are reducing our computational power. That's what is called periodic boundary condition. So here we need to realize one thing: in order to make our flow domain, very first important thing required, that's what is to make the blade. So up till say week 11, what all we have discussed, that's what is in sense of our preliminary design. Based on preliminary design, we have come up with the blade and blade geometry at different stations. Now that we are putting in terms of say coordinates, maybe x, y, z, or you can convert that into r theta plane, r theta z plane. This we will be putting as an input in order to make the solid blade. Okay. Now once we are ready with our blade, when we are doing our CFD analysis, that blade we need to consider as a hollow portion, and remaining portion, that's what is of our interest, that will be solid. So just understand one thing here, this blade what we are talking of, that's what is a hollow passage, and remaining flow domain, that's what will be a solid passage, and that we will be dividing into number of elements. So let's try to look at what all we need to do here in terms of discretization. So here if we look at, this is what is representing one of the blade, and around this blade if we look at, we are having systematic arrangement of these elements. That's what we can say structural mesh. We can have unstructured kind of configuration. You can see here, this is not systematically been arranged as we can see here. There are some configuration in which we will be having combination of both structure as well as say unstructured mesh. That's what we are defining as a hybrid mesh. Now meshing of rotating element in order to do CFD analysis, that's what is most challenging and complex task. Now when we say we want to analyze say stage, compressor stage, that's what is comprising of rotor and stator. In order to do meshing, one can do meshing within hours, one can take maybe day, maybe very intelligent or maybe very specific person who is planning to analyze the flow domain, he may take maybe week. Now the question is what all they are doing. Suppose say randomly without understanding what mesh I will be using say commercial package available or say some code, that's what is available, straightway if we are applying, that also will be discretizing our domain, and that also will give the solution. But the thing is, what exactly we are looking for, what is the purpose of doing CFD analysis, that's what is very important. So if we consider, we know very challenging task for us is to analyze what is happening around my blade on suction surface as well as on my pressure surface. Same way, what is happening near my hub surface and what is happening near my tip surface, or what is happening in a tip region, that's what is of our interest. What is happening between stator and rotor, that is also of our interest. Now if we are having this kind of understanding, what exactly we would like to analyze, based on that we need to do say meshing. Now meshing, that's what we can use say quad mesh, hex mesh, tri or tetra mesh, or maybe prismatic kind of elements, that's what will be used for the generation of say grid. We can say mesh, we can say grid, both the things are same in terms of terminology. Now there are two possibilities what we have discussed. That's what is say structural mesh and unstructural mesh, or structural grid and unstructural grid. So we can say structural in the sense this is what is most suited for well defined geometry and more difficult to generate. Suppose if we consider we are having say our fan blade or compressor blade, that's what is having three dimensionality in its shape, because we are having our blade angles at entry and exit, that's what is varying along the span, and that's what is giving the three dimensionality to our blade. Now in order to mesh this kind of blade, or in order to make such kind of domain, yes, this is what is challenging task. It is easier to control near wall clustering of cells, more accurately captures the boundary layer phenomena. We will see what is the meaning of that. By having say cells with largest aspect ratio around the sharp leading edge, it will provide better resolution in that particular area. So if we consider when we are using say transonic kind of aerofoils in which we are having sharp leading edge, even we are having sharp trailing edge, there in order to capture the details, it is more important to have such kind of structural configuration, and it requires comparatively less memory. Now when we are talking about the unstructured grid, it says it is intended for the complex geometries. So there are some complex flow study what we are doing in order to analyze the flow field for say fan as well as compressor. Under that configuration, we will be going with the unstructured kind of meshing. It is easier to generate, not much control, that's what is possible near the end wall region. It is easily automated. Typical flow if we are looking at say near the blade tip region, areas involving the leakage flow or secondary air system, film cooling, be casing treatment, all those kind of configuration where it is little difficult to do meshing with a small dimension. Under that configuration, we are going with say unstructured mesh. So here this is what is a very good example, that's what is given in one of the thesis. Here this is what is representing our structural grid configuration at the exit of stage, and this is what is say unstructured mesh kind of configuration. Here if we look at this whole domain, that's what is been used with say unstructured kind of configuration, and near this tip region, that's what is a prismatic kind of configuration they have used. So this is what is representing say non-dimensional axial velocity contours. So if we look at here for say structural configuration and unstructured configuration, the difference in the result can be clearly observed. So now the situation is what kind of flow field you want to analyze, that's what is giving you idea what need to be your meshing. That's why I said maybe within few hours also you can mesh, maybe it will take days for doing the mesh. Okay, so this is what we need to understand. Now in order to analyze this part, what we need to do is, suppose if I say I am having, this is what is one of my blade, there are different methodology, that's what is being used by different packages. I say commercial packages as well as say for individual industries, design industries, they are having their own codes. That's what will be used by them in order to generate the mesh. So mainly for universities we can say maybe some professors, those who are working with the coding, they may be making code for doing meshing, or maybe the students and faculty, they need to go with the commercial packages. So what they are doing, they will be dividing the whole flow field into blocks. Okay, so here in this case, this is what is representing the blade block, and this is what is representing my passage block. There is one more terminology, that's what is being used, it is called grid topology. We will see what exactly is the meaning of this grid topology. Now in order to analyze the flow between two blade passages, there are different methodology people they are opting for. Let's see one of the method, what it says, the flow passage between two blades, say suction side of one blade to the pressure side of the next blade. So just realize, suppose say this is what is my blade. Now in order to analyze this blade, What we can do, we can put our blade at the center and we can have this kind of say pitch configuration. So half pitch we will be putting here, half pitch we will be putting on the other side, and this is how we are analyzing the flow. There is one more possibility in which you can make your blade passage say one of the sides. Suppose if you consider here on say left hand side, you can take your pressure surface or suction surface. On right hand side, you can take your pressure surface and suction surface. So within the blade passage also can be analyzed. So now it's your choice how you want to do analysis. This is what is very important. So some of the papers when you are referring, they are opting with the different methodologies. So we need to be very careful about that. Mostly when we are analyzing the rotor and stator configuration, we are opting with this second option. It says complete blade inside the periodic flow passage. So this is what is my periodic flow passage in which we are putting our blade. Okay. Now in order to realize or in order to make the systematic mesh, we need to go with certain topology. So topology is nothing. Here you can understand this is what is representing my topology at the shroud region. This is what is my topology at say mid region. Topology in the sense we are making the basic framework. So here what magenta color you are observing, that's what is representing my topology kind of configuration. So we can say we are looking for doing the mesh, or say we need to discretize this domain using these blocks. Okay, that block we have defined, that's what is say passage block, and second we have discussed, that's what is say blade block. So blade block, it is nothing from, that's what is say from leading edge to the trailing edge, and my passage block, that's what is for say inlet to outlet with a periodic surface. Now this topology, that's what is invariant from hub to shroud and edited on the 2D layer located at various spans. So you can understand what we have discussed. Say suppose say this is what is my blade. Now this blade I can divide into number of layers. So here you can see this is what is representing one of the layer. Like this is what is similar to what we are doing in terms of design. What we have done, we are dividing our span into number of stations. Same way when we are making our mesh, we will be taking different layers. Now for that layer we will be making this topologies or these blocks. What it will be doing, when we will be doing our meshing, that time it will be taking care of the meshing in a systematic way with increase and decrease of size of these elements. That's what is a benefit. So whatever tool we are using, if we are having thorough understanding, suppose say this is what is one of the challenging aspect, that's what is tandem bladed rotor, what we were discussing in week 3 also. So here in this case, my interest is near my leading edge, what flow is happening. Same way the leading edge of my second blade and the trailing edge, or say the exit of my first rotor blade, that's what is of my interest. Same way exit also we are looking for in terms of what is happening. We can understand we want to analyze the effect of change of incidence angle. We are looking for studying the flow physics in terms of wake formation because of presence of trailing edge. Under that condition, this is what is very helpful to us. Without blocking also you can do your meshing, but it is preferred when you are doing the meshing for this axial flow turbomachinery, let it be say axial flow compressor, axial flow fan, or say axial flow turbine, we will be adopting this kind of configuration. Okay, so there are some commercial package in which ready-made they are making these blocks. With that understanding, even using other meshing tools also you can make your say blocks and you can analyze the flow physics. Now we need to be very careful when we say refinement of mesh is a part of layer. So we will be doing refinement, or maybe we will be changing the size of the element, everything. That's what is within this blocks. It is nothing to do with the topology. Be careful about this part. Now we can say once we have made this block or topology, what will be our next step? So now we need to select what kind of grids or mesh elements we will be selecting with. So here in this case, if you look at carefully, say this is what is our blade. Now surrounding of this blade, we are having very fine mesh we can observe. That's what is to capture the growth of boundary layer. Just understand what is happening on my suction surface and what is happening on my pressure surface. That's what is of our interest, because that's what is representing my work done capacity by individual aerofoil. Suppose if I consider say blade, it is comprising of number of such aerofoils. So for each aerofoil we need to have these details to be available. So in order to do that part, we need to have great control in terms of Y plus. So you may be aware of Y plus, okay. That's what is one of the method in order to make measurement or in order to make the element near to my blade, okay. So this is what is representing the Y plus value. It provides near orthogonal elements on the blades. So this is what is one of the grid which we can use in order to capture the boundary layer behavior on suction surface as well as on the pressure surface. Now next configuration or next kind of grid, that's what is say J grid. So here if you look at, this is what is having J shape, okay. What it says, it is usually used near leading edge and trailing edge. It wraps in opposite direction at leading edge and trailing edge. So this is what you can say, it is making J shape. Same way here if you look at, this is what is making J shape. That's what is say J kind of topology or J kind of grid. Okay. Now after doing the refinement near end wall region or say near the blade region, now remaining portion, that's what need to be filled with the elements. And in order to do that, we will be using say H kind of grid configuration. So structural block, that's what is extended from upstream to leading edge, downstream of the trailing edge, and in between the blade and the periodic surface. So here if we look at these all elements, these elements are H grids, okay. Now there are say typical kind of blade analysis, suppose if we are looking for. So this is what is one kind of typical configuration we can say. So upstream and or downstream ends do not have one-to-one periodicity. Here in this case, this periodicity and this periodicity, that's what is not same. Under that configuration, L grid, that's what is being used. It is not being used for multiple blade systems. So suppose when we are analyzing cascades, so we have seen cascade, you can understand that's what is say 2D, but in order to analyze the secondary flow field, we are using that for 3D analysis also. So for specially cascade kind of blades, this kind of configuration, that's what is being used. That's what is called L grids. Now this is what is representing the C grid. The another way of topology, that's what is provided near the leading edge and trailing edge. So here this is, you can see, this is what is a C kind of configuration, okay. So all the above topology, that's what is been used along with O grid with proper resolution in order to capture the boundary layer growth. So O grid, that's what is very important, and that's what we are putting surrounding to our blade. So proper resolution of leading edge and trailing edge radius, that's what is very important. So establishing say grid independence or insensitive, that's what is a standard practice. So we will be discussing what is the meaning of grid independence study or grid resolution or grid insensitivity study. So here if you look at carefully, this is what is representing the blades, and here you can say we have systematic gridding, that's what has been done near our say hub surface. Same way this is what is representing what is happening along the span. So we can say this is what is a passage block, and near say this is what is of our interest near the tip region, what is happening. In order to capture the tip leakage flow, we are looking for such kind of elements, okay, and this is what is representing the periodic surface, okay. Now there are certain thumb rules what people over the year they have defined with, and that's what is called a best practice guideline for the meshing. Let's see what we realize for that. So it is very difficult initially that we will be deciding with what will be the size, because we need to understand what is the purpose of simulation. As we have started initially only, I told the same thing. We must understand what exactly we want to analyze. Okay, so it says when we are having 2D in viscous simulation of one blade, mesh with 3000 cells is most sufficient for. So you can understand when we are analyzing say potential flow configuration, under that condition we can use 3000 cell, that's what is more than sufficient. When we are going with the 3D in viscous blade simulation, you need to go with say 40,000 cells, that's what is sufficient. Now this is what was earlier analysis. These days also people they are analyzing using say in viscous simulation for getting some of the idea in terms of what is happening with the flow. Okay. Now on in viscous Euler simulation, it is say it should be fairly equal to the size and no boundary layer resolution, that's what is required. So we can understand we are not interested, or say it will not give you details what is happening on the surface of my blade, both on suction surface as well as pressure surface, and that's the reason why we are not bothering of say you having say more number of elements in that particular region. Now in order to do say loss prediction, where growth of boundary layer and the separation, that's what is very important, under that configuration your boundary layer resolution, it is very important. Okay, so boundary layer resolution can either be coarse and suitable for the small Watt function when we are using say low Reynolds number. So basically when we are analyzing the flow over our blade surface, maybe rotor surface or say our say stator surface, we are mainly going with the 3D simulation, where we are using say wall function mesh. There we are looking for say around 1 lakh cells, 1 lakh elements. This type of mesh, that's what is suitable for the initial design. So suppose say you have made your blade, or you have done your preliminary design, you made your blade and you want to analyze that blade quickly. Under that configuration, small number of cells, that's what is sufficient. But this is what is not giving us idea in terms of secondary flows or the formation of vortices. Now the question is, when we are looking for such kind of flow field analysis, when we are going for detailed analysis, under that configuration we need to have the resolution near this blade region, and for that 4 lakh cells, that's what is required. Say for good low Reynolds number resolution, we need to go with say 10 lakhs element, that's what is say 0.1 million elements, that's what we need to analyze with. So 2D simulation also people they are using for initial analyzing. For that 20,000 cells, it is good for say low Reynolds number mesh, but when we are moving with say analyzing of boundary layer growth, we need to increase the number of elements. Now all these things what we are discussing, that's what will be coming in terms of selecting the number of blade, number of elements. Suppose if we consider we want to analyze the flow in detail near the leading edge and the trailing edge, then we need to use more number of elements in that region. Suppose say we are having blunt kind of configuration, suppose say we are analyzing say turbine, say our gas turbine leading edge, that's what is having say rounded edge, rounded leading edge. Under that configuration we need to go with more number of elements. So basically some thumb rule, some idea that must be there with us when we are analyzing or say when we want to do CFD analysis. Again, the question is how many number of elements what we are using. Basically it depends on what kind of analysis we are doing. Okay. Now it says when we are facing difficulties in sense of say conversions, sometime this coarse mesh, that's what has been preferred near the trailing edge. So this is what is say when we are doing our analysis and we are not getting the solution in a proper way, then sometimes mesh need to be modified. When we are doing this kind of configuration, it will not give what physics what we are looking for. Okay, this is what will be used, but this is giving us say low resolution or low accuracy of the results. Now, so design iteration type simulation, when we are looking for, we need to set with y plus value. Now this y plus value, it says that need to be in the range of 20 to 200. When we are analyzing say low Reynolds number kind of configuration, this maximum y plus value should be as low as possible. So more precise results when we are looking for, this y plus value need to be in the range of 1 or below 1. So there are some commercial calculators which are available, in which you can put your Reynolds number as one of the parameter with some flow properties. It will give you the calculation of y plus. This y plus you will be putting in order to analyze or in order to calculate the value of y plus. That y plus value we will be using for making of layers near the blade surface. Now outside say first cell, now when we have calculated our y plus value, then we need to move in say direction of periodic surface. That expansion or say growth rate, that's what need to be kept in the range of 1.24. So let me show you here. Suppose say when we are looking this kind of configuration, here near the blade surface where we are having say number of elements to be very high, and progressively that's what is going to increase. So that's what is called growth rate, and it says that need to be in the range of 1.24. Okay, so the rule of thumb, the wall mesh typically required in the range of 5 to 10 when we are having boundary layer to be captured with. When we are looking for say resolve low Reynolds number kind of configuration, more number of elements are required near the boundary layer. Now over the year with experience, one will learn all these aspects. We were discussing about say one parameter we have defined as a mesh sensitivity. Let's see what exactly is the meaning here. So in order to check, see number of elements we have discussed, sometimes it says maybe 3 lakhs or 4 lakhs elements, that's what is sufficient. It says more than 10 lakhs elements are required when we are looking for special kind of analysis. That's what is all depending on the size of my blade. So when we are doing this analysis, what elements I have selected, that should not change the result. So for that, different researchers, they are opting with the different approaches. So one of the approach you can see here, this is what is for say one of the transonic compressor, that's what is designed for pressure ratio of 1.4. Here under this condition, say initially flow domain, that's what is being generated. Then for that flow domain, say coarse mesh, medium mesh, intermediate mesh and fine mesh, 4 different kind of meshes they have been analyzed. And here if you look at say all this domain, that's what is been run or simulated for different mass flow configuration. And here if you look at for say intermediate and fine mesh, we are not having change of results both in terms of pressure rise as well as in terms of efficiency. So this is what is called grid independent study. So this is what is required whenever we are discussing our result, when we are representing our results in say conference or paper or say maybe talking to industries. That time in order to build the confidence, this is what is very important. So very first question when we are analyzing say initial start with say design, there is nothing to worry for. But when we are doing that systematic analysis, this is what is very important. You need to analyze, that's what is called grid independent study. So you need to go with increasing and decreasing the number of elements. So here intermediate and fine mesh, if we configure, suppose a fine mesh, that's what is required, more number of elements, rather with less number of elements, if we are getting similar kind of trend and result, then we will be going with the intermediate mesh. So this is what is very important. One more trend, what people they are doing, say along the span, they are measuring say total pressure rise. So here in this case, this is what is representing say different number of elements which are being selected with. So particular element when we are selecting, that's what is not changing my result. So this is also one of the way in order to select the mesh. Same way, suppose if we consider we are looking for say study in which we can take our CP distribution at mid station, near the hub and near the tip region for say analysis purpose, we will be doing say mesh sensitivity analysis or grid independent study at that particular location, and when we find with increase or decrease of number of elements, if my results are not changing, that's what we will be selecting for the further study. So this is what will give you the confidence to be built. Now many times what happens, say we already have some experimental results available with us. Now with those results, if we want to analyze, then we need to do the parametric study, that's what is called validation. So if I'm having, suppose say for this compressor, I will be having my experimental results, so I will try to match my computational results and experimental results with different mesh, and then we can prove that's what is say independent of grid size, and that's what will be the helping hand. So this particular week, that's what is dedicated for CFD application to design and performance assessment. So we need to understand what exactly we mean by design and what exactly we mean by performance assessment. When we say, again let me tell you what CFD we are discussing at this moment, this is not the design tool. This is what is for assessment of design. So with this we are stopping here. Let's see. So very first aspect for CFD analysis, that's what is say discretization of domain. So we have discussed a lot of details in terms of selection of say elements, type of element, number of elements, grid independent study. That's what will be giving us more detailed idea. So many of you are using commercial tools, or many of you are using your already available in-house codes. Just try to read, just try to understand what we mean by all these terms. This course is not for CFD, and that's the reason why we are not going into more detail. You might have done the CFD course maybe in your earlier study, or maybe you will be doing that course. That time this will give you more accurate understanding in terms of what we say discretization. So thank you very much. See you in the next lecture.